everyone, and welcome to Calculus. Today we are studying the integration of inverse trigonometric functions. These are especially difficult because when you first see them, you might not be thinking inverse trig. You might just be looking for a way to solve it. So if you were given this one on a test of mixed integration where it wasn't specifically designed for integration of inverse trig functions, you might sit there and say, oh, it's u is equal to 1 plus 9x squared. But then when you tried to do du, you would get 18x. And while you can add an 18 to the problem, you can't add that x. That's not allowed, so don't do that. Or you might be thinking, well, then I've got to move it to the top. 1 to the negative 1 plus 9x to the negative 2. Okay, that's just wrong on so many levels. I'm not even going to talk about why. So this needs to kind of be in the back of your mind as something that you can go to when you can't figure out how to integrate. They unfortunately do not come up very often, so it's hard to get used to them. But you're looking for one of these three patterns. I don't see a square root, so I jump straight to tangent. And sure enough, if I let u be equal to 3x, then u squared would be 9x squared. And I could rewrite this as 1 plus u squared. Now I still have a dx. So du is equal to 3 dx. I don't have a 3 dx. I think you guys are getting used to this by now. So the 3 and the 1/3. So I have the 1/3 on the outside, and the 3 dx is my du. That gives me 1/3, and now that I have this exactly the way I want it, it is just 1/3 inverse tangent of u, which is 1/3 inverse tangent of 3x plus c. If you would like to go ahead and try some of these on your own, this is another one where I'm going to go through each one, but you really, if you can do these on your own, then by all means, go for it. That's the answer to number 2. This is the answer to number 3. You can go ahead and screenshot those. Number 4 is inverse sine of x over 3. Number 5 is inverse sine of x over 5. Number 6 is pi 12ths. Oops, that looks like pi halves. It is pi halves. Pi 12ths. And number 7 is a challenge. I will tell you the answer is pi halves. I'm not going to give you any hints on it. See if you can do it. Okay, number 2. So I look back at my list and I see that there are 2 types of square roots. One where there's something on the outside and one where there's not. So in this problem, I don't see anything on the outside. So I'm thinking that it's going to be sine. If it is sine, I'm just going to write it on this paper so you can see it handy. U squared du is equal to inverse sine. So since I think it's sine, I need a u squared. So if u squared is going to be this x to the 6th, then u must be x to the 3rd. Sometimes people think that they don't have a perfect square there. Remember that with exponents, you add them. So x to the 3rd times x to the 3rd is x to the 9th. X cubed, sorry, is x to the 6th. It's not the 9. So x to the 3rd squared is x to the 6th. Interestingly enough, x to the 9th does not have a perfect square. So 9 is a perfect square, but as an exponent, it's not. Exponents just need to be even to be perfect squares. And then du is equal to 3x squared, which is a lucky thing since I have an x squared. I don't have the 3 though, so I am going to put the 3 in the problem. And now I can rewrite it. The 1/3 is the constant. The integral is still there. This whole piece, 3x squared dx, is my du. And now I have the square root of 1 minus u squared. Sometimes people don't like to show this next step. They like to jump straight to the answer. But you should take just a minute and write the u and then write the answer. It doesn't take that much more, but it does sometimes cause trouble for people. Inverse sine of x cubed plus c. All right, we've talked about how when there's two e's in a problem, then one is going to be u and one is going to be du. But in this case, I have, even if I thought to do this, so if this was not in this section, I mean, in this section, you know you're looking for inverse trig. But if this wasn't inverse trig, think of, you might have tried making the whole entire denominator equal to u so that you can get that du over u natural log thing going on. But look, the derivative of e to the 4x would be e to the 4x. So that's another way to know that it's not going to be this, because this is squared. Again, not a square that you're used to doing, but e to the 2x times e to the 2x, you add their exponents, is e to the 4x. So if you make u e to the 2x, then u squared would be e to the 4x. So I'm going to let that happen. And then my du would be e to the 2x times the derivative of the 2x times 2. I don't quite have that. I'm missing the 2, so I add the 1/2. Now I rewrite the equation with the u's. I do expect to see this step. Can't just skip it. So this, and this is my du. And on the bottom, I have 1 plus u squared. This is the formula for tangent, inverse tangent. Inverse tangent of u. And now I can replace the u back. Inverse tangent of e to the 2x. You don't have to have the parentheses around that. If you have them, you can, but it's understood that it goes together. This next one's a little bit tricky. So I actually have two in a row that are almost identical, so that after I show you number 4, you could maybe stop the video and try number 5 on your own. So what makes this one so tricky is that you may recall that in order to have this be the sign, actually I'll just back up to it. In order to have this be the sign, I need 1 minus u squared. I need 1 for all of them. So in order to make that a 1, you're gonna have to work at it a little bit. So dx over the square root, I'm actually gonna have to factor the 9 out in order to make that a 1. When you factor the 9 out, you're left with x squared over 9. Think about that, redistribute. 9 times 1 would be 9, and 9 times negative x squared over 9, the 9's would cancel and you'd have x squared. And then just like you've always done, breaking things into parts you can do and parts you can't, you're going to break this down into a part you can do and a part you can't. And then you can actually simplify the square root of 9, which is 3, dx over 3 square roots of 1 minus x squared over 9. So that's the step you need to do before you can even start, okay? All right, once you get there, then you have to ask yourself, what is my u? So u is going to be x over, careful, 3, because that would give me the u squared is equal to x squared over 9 that I see there. Du, if I did that, is, remember, x over 3 is the same as 1/3 x. But it's easier for people to take the derivative of 1/3 x. So if you ever need to change that, go ahead and do it. The derivative is 1/3 dx. So fortunately, I have a 1/3 dx. So this is going to become the integral. The dx over 3 is my du. And my square root of 1 minus, and that's my u squared. This is inverse sine of u. And my final answer, you always have to replace the u back, is inverse sine of x over 3, or 1/3 x, whichever you like better. Okay? So you might want to try number 5 on your own and see if you can get it. But of course, I'm going to do it for you. You know I am. So again, I'm going to rewrite this. I'm going to factor out the 25 so I can get 1 minus x squared over 25. That gives me 1 over 5 square roots of 1 minus x squared over 25. There's still a dx. Try and keep your notation better than mine was. So I'm going to let u be x over 5. That way my du will be x squared over 25. Not my du. My u squared. And my du, remember this is the same as 1/5 x. So it's just 1/5 dx. And I have a 1/5 dx. It's perfect. So the 1/5 dx is going to become the du. And then I have the square root of 1 minus u squared, which is by definition the inverse sine of u. This is actually the step that I was complaining that sometimes kids skip. U, at this point, still u, and then your final answer will be inverse sine of x over 5 plus c. So I know you're looking at number 6 and saying, what are those square root of 2 and 2 over the square root of 3 doing there? So you can just ignore them for now. I am going to teach you how to do them, but you haven't done it yet. So basically, this is just your secant formula. It is literally exactly your secant formula. You don't need to use u substitution if your du is exactly equal to your dx. You can just jump straight in. So this is going to be inverse secant of x. Now here, when you see these two little things written here, that means we don't do plus c. We do a really cool thing. We change our integral symbol to a line and we put it on the other side. And then we write the two things again. They're called the limits of integration. So there's my square root of 2, and here's my 2 over the square root of 3. And then you plug them in one at a time. Plug in the top, minus, plug in the bottom. I know this absolutely means nothing to you at this point, but it actually has a very cool meaning. It is the whole purpose behind integration, but right now we're just going to focus on the skill, and later we'll focus on what it means. So inverse secant of square root of 2 minus inverse secant of 2 over the square root of 3. So you need to be thinking to yourself, when is secant the square root of 2? Well, secant is equal to the square root of 2 when cosine is equal to 1 over the square root of 2, or the square root of 2 over 2, right? Do you know when cosine is the square root of 2 over 2? At pi fourths. And same thing for this one. If you don't recognize it right away, when is secant 2 over the square root of 3? When cosine is the square root of 3 over 2. Do you remember when that happens? That happens at pi 6. Of course, these aren't the same, so we need to get a common denominator, which would be 12. So in twelfths, 1/4 is the same as 3/12, and 1/6 is the same as 2/12. So 3 pi twelfths minus 2 pi twelfths is 1 pi twelfth. So when you see these little things at the top and the bottom of an integral symbol, that simply means that you need to do a little more work, because otherwise we would have been done right here. Inverse secant, done. All right, so this one is a challenge. I'll show you how to do it. It has a trick to it. The challenge is that you need to complete this square. So if you rewrite this as x squared minus 2x plus blank plus 2 minus blank, this is really bringing back from the past, then you break this in half. So minus 2 divided by 2 is 1, and then I square it. Negative 1 squared is 1. But you can't just add a 1 to your expression, so I'm also going to subtract a 1. This expression, x squared minus 2x plus 1 plus 2 minus 1, is equivalent to this one. I haven't changed it, but now this piece becomes that, and this piece becomes a 1. So I can rewrite this as x minus 1, the quantity squared, plus 1. Which now I'm going to just reverse. Why did I reverse it? So that it would look like tangent. Notice that there's no square roots. So the only one that doesn't have square roots associated with it is the tangent. Inverse tangent of u. So my u must be x minus 1, but my du is just dx. Whenever that happens, you actually don't need to bother with u. You can jump straight to the answer. So 1 over 1 plus this u squared is inverse tangent of the x minus 1. You can jump straight to that because the du is equal to the dx. Now, normally we would write plus c and be done, but whenever you see numbers at the top and the bottom of the integral sign, that means you're not done. So I'm going to go from 0 to 2. Believe it or not, even though the top one, people think about the top one being first, we say the integral from 0 to 2. So that's going to be inverse tangent of 2 minus 1. So you plug in the top one, plug in the top, minus inverse tangent of, now you plug in the bottom, 0 minus 1. This is inverse tangent of 1 minus inverse tangent of negative 1. So what you have to do is ask yourself, when is tangent equal to 1? Tangent is equal to 1 at pi fourths. When is tangent equal to negative 1? So tangent is equal to 1. Tangent of pi fourths is equal to 1. Tangent of 5 pi fourths is equal to 1. But nobody writes that. Everybody knows that they give the quadrant 1 answer. But what about this one? Does anybody remember if it's the quadrant 2 answer? So tangent of 3 pi fourths is negative 1 because of forecast. Right? Tangent's only positive in the all quadrant 1 or in quadrant 3. Here, tangent of negative pi fourths, you can write 7 pi fourths, but when you're doing an inverse tangent, we just go from 0 is equal to negative 1. And that is what it is. They want the quadrant 4 answer for inverse tangent. So quadrant 4 would be negative pi fourths, which is pi fourths plus pi fourths, which is 2 pi fourths, which was the answer of pi halves. All right. Have a great day, everybody.